So we now discuss ionic equilibria. First we want to know what is electrolytes. So substances like acid, base and salt which can conduct electricity in the aqueous solution due to ionization are known as electrolytes. Upon the extent of ionization, the electrolytes are divided into two classes. One is strong electrolytes, the substances which ionize almost completely into ions in aqueous solution are called strong electrolytes like HCl. Examples are HCl, H2SO4, NaCl, NaOH, HNO3, etc. And the next one is weak electrolytes, the substances which ionize to a small extent in aqueous solution are called weak electrolytes. For example, acetic acid, ammonium hydroxide, hydrogen cyanide, etc. Next we discuss acid-base concept. So first is Arrhenius concept of acids and bases. According to Arrhenius concept, an acid is a substance which dissociates in aqueous solution to give hydrogen ions or H plus, and base is a substance which dissociated in aqueous solution to give hydroxyl ions or OH minus. The ionization of an acid HX in water can be represented as, so HX goes to decomposes into H plus X minus, or HX plus H2O in solvent H2O, it forms H3O plus ion and X minus ion. Similarly, the ionization of a base MOH can be written as MOH in aqueous solution gives M plus ion plus OH minus ion. Next we discuss Bronsted-Lowry concept. According to this concept, an acid is a substance which can donate proton or H plus, while a base is a substance which can accept a proton or H plus. In other words, acid is a proton donor and base is a proton acceptor. For example, HCl in aqueous solution and ammonia in aqueous solution, so H plus ion from HCl is taken up by NH3, so gives NH4 plus ion and chloride minus ion. So in this above reaction, HCl loses a proton and is an acid. So since HCl is donating a proton, so HCl is an acid, whereas ammonia accepts a proton and is a base. There are certain substances such as water, HCO3 minus bicarbonate ion, etc., which are capable of donating as well as accepting the proton. These substances are called amphoteric substances. For example, water behaves as an acid as well as base. So as a base, HCl when dissolved in H2O, so here H2O acts as a base because it accepts a proton from HCl and it forms H3O plus ion here and chloride minus ion. And as an acid, H2O when ammonia is dissolved in water, so we get ammonium ion. So here H2O actually accepts a proton from here and gives ammonium ion accepts a proton from H2O. So H2O gives a proton here, donates a proton here, and it forms ammonium ion and OH minus or hydroxyl ion. Next is conjugate acid-base pairs. The pairs of acids and bases which are formed from each other by the gain or loss of a proton are called conjugate acid-base pairs. For example, HCl here aqueous solution, so hydrochloric acid when reacts with ammonia here, ammonia is base, so HCl loses a proton here and gives Cl minus, so Cl minus is a base here, and here ammonia NH3, it is a base here. When it accepts a proton from HCl, so we get ammonium ion. So now ammonium ion can act as an acid. From the figure, it is clear that HCl donates a proton and forms Cl minus ion, which has a tendency to accept a proton. Similarly, ammonia accepts a proton and acts as a base, but it forms NH4 plus ion, which has a tendency to behave as an acid. The base formed from an acid is referred to as the conjugate base of the acid. So Cl minus is the conjugate base of the acid HCl. Similarly, the acid formed from a base is called conjugate acid of the base. So here NH4 plus ion, here it can donate a proton and the corresponding base is NH3. So NH4 plus ion is the conjugate acid of the base NH3. Thus in the above example, Cl minus or chloride ion is the conjugate base of acid HCl and NH4 plus is the conjugate acid of the base NH3. Next we discuss relative strengths of conjugate acids and base. According to Bronsted-Lowry concept, the strength of an acid depends upon its tendency to donate a proton and the strength of a base depends upon its tendency to accept a proton. So according to this, a strong acid means a good proton donor and a strong base means a good proton acceptor. To summarize the relative strengths of conjugate acid base pairs, so strong acids has a weak conjugate base. So HCl here is a strong acid, so the conjugate base Cl minus is a weak base. Weak acid has a strong conjugate base. Strong base has a weak conjugate acid and weak base has a strong conjugate acid. Now what are the advantages of Bronsted-Lowry concept over Arrhenius concept? So it can explain the basic character of substances like Na2CO3, NH3 etc. which do not contain any hydroxyl ion, because according to a Arrhenius theory or Arrhenius concept, the substance which can donate proton is an acid and the substance which can donate OH minus or hydroxyl ion it is called base, but in Na2CO3 and NH3 there is no OH minus ion, but still they are called base. Bronsted-Lowry concept is not limited to molecules but also covers the ionic species to act as acids or bases. So Bronsted-Lowry concept can explain the acid-base reaction in the non-aqueous medium also. But what are the limitations of Bronsted-Lowry concept? It cannot explain the reaction between acidic oxides like CO2, SO2, SO3, etc. and basic oxides like CaO, BaO, MgO, etc. which take place even in the absence of solvent. Similarly, substances like BF3, Al, Cl3, etc. are known to behave as acids, but they do not have proton to donate. So we cannot explain these phenomena using Bronsted-Lowry concept. Then comes Lewis concept of acids and bases. According to this concept, an acid is a substance or molecule or ion which can accept a pair of electrons, while a base is a substance which can donate a pair of electrons. So A is Lewis acid and B we call Lewis base. So the B contains a lone pair, of donor electrons here. So when it donates to A, then we call that A is Lewis acid. So we get AB here. Yeah. In other words, acids are electron pair acceptors while bases are electron pair donors. Thus, it is evident that any substance which has an unshared pair of electrons can act as Lewis base, while a substance which has an empty orbital that can accommodate a pair of electrons form Lewis acid. According to Lewis concept, the following species can act as Lewis bases: neutral species having at least one lone pair of electrons. For example, NH3, we know NH3 nitrogen contains a lone pair of electrons here. Amide here, then ROH, etc. Negatively charged species or ions, for example, Cn minus, Cl minus, OH minus, etc. So they act as Lewis bases here. And the following species can act as Lewis acid: molecules in which the central atom has incomplete octet, for example, BF3, AlCl3, FeCl3, etc. Simple cations can act as Lewis acids, for example, Ag plus, H plus, etc. Molecules in which the central atom has empty d orbitals, for example, SiF4, PF5, SnCl4, etc. So what are the limitations of Lewis acid concept, Lewis concept? Lewis concept is too general and includes all the coordination compounds and coordination reactions. This, however, may not always be true. It does not explain the behavior of well-known protonic acids like HCl, H2SO4, etc., which do not form coordinate bonds with bases. Like here we discuss the coordinate bond here. Okay, so that we cannot explain using Lewis concept. Acid-base reactions are usually fast, but the formation of coordination compounds is slow. It also cannot explain the relative strengths of acids and bases. The catalytic activity of many acids is due to H plus ion. Since a Lewis acid need not contain hydrogen, therefore, we cannot actually explain those behavior using Lewis concept. Next, we discuss ionization constant of water and ionic product of water. Water is a weak electrolyte and undergoes self-dissociation to a small extent as, so H2O, 2 moles of H2O, when dissociated, it forms H3O plus ion plus OH minus ion. The dissociation constant for the ionization of water, if we call K, this is the product side. So H3O plus concentration of H3O plus times concentration of OH minus by concentration of H2O raised to the 2. Since the degree of dissociation of water is very small, the concentration of undissociated water may be practically taken as constant. So now we consider, so K times H2O raised to the 2 is equals to concentration of H3O plus times concentration of OH minus. So this quantity K times H2O raised to the 2 we call Kw. Kw is a constant term and is known as ionic product of water. So here where Kw is a constant, as I mentioned, and is known as ionic product of water, its value is constant at a particular temperature. So value of Kw depends on temperature and varies with the change in temperature. At 298 K, the value of Kw is 1 times 10 raised to the minus 14 mole raised to the 2 liter raised to the minus 2. So it is quite evident that the concentration of H3O plus and OH minus are equal in pure water, right? So pure water, so you see how it dissociates. So when 2 moles of H2O liquid dissociates, it forms 1 mole of H3O plus and 1 mole of OH minus. So the concentration of H3O plus and OH minus are the same in pure water. So Kw we can write as 1 times 10 to the minus 14. So if we do it, so instead of concentration of OH minus and H3O plus here we can actually replace concentration of OH minus by H3O plus, because concentration of H3O plus and OH minus are the equal. So we get concentration of H3O plus is 1 times 10 to the 7 moles per liter. The density of pure water usually 1 gram per centimeter raised to the 3 or 1000 grams per liter, and its molar mass is 18 gram per mole. Therefore, the molarity of pure water can be given by this. So concentration of H2O, this per mole if we consider, so we get 1000 by 18, so we get 55.5. So the molarity of pure water is 55.55. Now we discuss the effect of temperature on Kw. So if we see this table here, as temperature increases from 273 to 373, we can see that the change in the Kw value. Okay, so the Kw value increases if we increase the temperature. So from this table, it is clear the value of Kw increases with rise in temperature. In accordance with the Le principle, increase in temperature will shift the equilibrium in the forward direction. Hence, Kw increase with rise in temperature. Next, we discuss what is pH. The pH of a solution is defined as the negative logarithm of the concentration of H3O plus. So in moles per liter unit. Okay. So in order to get the pH value, we need to express the concentration of H3O plus in terms of moles per liter. And mathematically, so pH is log, here base is 10. Okay, remember base is 10 here. So it's not base E, base is 10 here. So log 10 base concentration of H3O plus. For neutral solution at 298 K, since concentration of H3O plus and concentration of OH minus are the same, and then we got the value 1 in times 10 raised to the minus 7 moles per liter. So we can calculate the pH of pure water at 298 K. So pH is minus logarithm of H3O plus. So concentration of H3O plus, so if we put, we get the value 7 here. And for acidic solution, pH is less than 7, and for basic solution, pH is greater than 7. Okay, so remember again, the base is 10 everywhere while calculating the pH of a solution. Like pH, pOH can also be defined as, so pOH again is minus logarithm of concentration of OH minus. Again, the base here is 10 base. Okay, so when we calculate pH and pOH, the logarithm the base of the logarithm is 10. But we just discussed that concentration of H3O plus times concentration of OH minus is Kw. So if you take log of both sides, so we get this side we get log H3O concentration of H3O plus times concentration of OH minus gives log Kw. So log this log A times B gives log A plus log B. So first term will be log H3O plus and the second term will be log OH minus. So if we do it, we get this. If we consider the minus sign, we get this is pH, this is pOH. So log 10 base H3O concentration of H3O plus gives pH, and log base 10 concentration of OH minus gives pOH, and this side log gives pKw. So at 25 degrees Celsius, pKw is 14. So pH plus pOH gives 14. Buffer solution, next we discuss the solution which resists changes in the hydrogen ion concentration on the addition of small amount of acid or base are called buffer solution. Human blood is an example of a natural buffer solution. So it can be acidic buffer. They contain equimolar quantities of a weak acid and its salt of strong base. For example, acetic acid and sodium acetate. Okay. So for acidic buffer, we have to consider the weak acid and its salt with strong base. So acetic acid is a weak acid, we know, and when it reacts with a strong base like NaOH, we get sodium acetate. So acetic acid and sodium acetate, they form a buffer or an acidic buffer. Okay. Next we discuss basic buffer. So they contain equimolar quantities of a weak base and its salt with a strong acid. So basic buffer means we need to consider weak base like ammonium hydroxide and its salt with a strong acid like ammonium chloride. Okay. So ammonium chloride, ammonium hydroxide when it reacts with HCl, we get ammonium chloride. HCl is a strong acid here. Now we discuss buffer action. The ability of a buffer solution to resist the changes in pH value on the addition of small amount of an acid or base is known as buffer action. Then we discuss Henderson-Hasselbalch equation. So consider the general equation of a weak acid and its conjugate base. So HA is a weak acid. So when we add water, so we get H3O plus ion and A minus ion here. So the dissociation constant of HA, if we call Ka, is concentration of H3O plus times concentration of A minus by concentration of HA. We don't consider H2O because we add H2O in large amount. So rearranging the above equation, if we rearrange and take the log minus log 10 on both sides, so we get minus log 10 concentration of H3O plus equals to minus log 10 Ka plus log concentration of A minus by concentration of HA. So this left hand side, again we already discussed, this is nothing but pH, and this is the value of pKa. pKa is the dissociation, Ka is the dissociation constant. So this is the value of pKa of that acid HA, and plus log concentration of A minus by concentration of HA. So we can actually calculate pH from the value of pKa of the acid, and if we know the concentration of conjugate base and the concentration of conjugate acid. So this is the expression. This expression is known as Henderson-Hasselbalch equation. So Henderson-Hasselbalch equation is pH equals to pKa plus log 10 base concentration of conjugate base by concentration of acid. Similarly, if we consider for bases, we will arrive at this expression. So POH is pKb. So the Kb is the again the dissociation constant of the weak base here. So POH is pKb plus log 10 base concentration of conjugate acid by base. Since pH plus POH is 14, so we can write pH equals to 14 minus pKb. So here we substitute the value of POH or by pH minus 14 here. So 14 minus pH here. So we arrive at this expression. Then we discuss solubility product. The solubility product, often denoted by Ksp, is the equilibrium constant for the dissolution of an ionic compound into its constituent ions in an aqueous solution. It represents the maximum product of molar concentrations of the resulting ions, each raised to the power of their stoichiometric coefficients in a saturated solution. For a general salt Ab dissolving as, so if we take salt Ab in aqueous solution, it gives A plus ion and B minus ion. So the solubility product expression is Ksp is concentration of A plus times concentration of B minus. We don't consider concentration of Ab because it is solid here. So for salt with more complex formulas such as A2B3, the expression is, so A2B3 if we consider instead of simple Ab that we considered just now. So A2B3 dissociates into 2 times A to the A raised to the A3 plus 3 B2 minus. So Ksp we get now A3 plus, and this is the stoichiometric coefficient, that's why you get the raised to the 2. So concentration of A3 plus raised to the 2 and concentration of B to the B2 minus raised to the 3. What are the applications of solubility products? So predicting precipitation reactions. We can predict precipitation reaction if we know the solubility product of a salt. Quantitative and qualitative analysis to determine the concentration of ions in solution. Ksp is crucial for designing compounds with controlled solubility in drugs formulation. Ksp principles guide the extraction of metals from their ores by predicting precipitation and solubility behavior. So what are sparingly soluble salts? So sparingly soluble salts are ionic compounds that dissolve in water only to a very limited extent, typically having solubility less than 0.01 mole at room temperature. So they established dynamic equilibrium between the solid phase and dissolved ions, and the solubility product Ksp governs this equilibrium. For example, BaSO4, AgCl, CaCO3, they are all sparingly soluble salt in water. So what are the properties? These salts dissolve only as little as possible, resulting in very low concentrations of their dissolved ions. Their solubility product is often affected by factors like temperature, common ion effects, and usually decreases with the addition of a common ion in solution. So what are the applications and importance? They are used for qualitative analysis of ions, such as identifying cations in a mixture by selective precipitation. Critical in water treatment, where compounds like calcium carbonate can cause scaling in pipes. They are important in pharmaceutical industries, since sparingly soluble drugs may need special formulations to enhance bioavailability. Used in medical imaging, for example, BaSO4 is used in X-ray diagnostics due to their safety. Help in managing industrial processes such as preventing precipitation or scaling issues in pipelines. Next we discuss dissociation or ionization constants of acids in water. So the dissociation equilibrium of an acid Ha can be represented as, so Ha plus H2O gives H3O plus A minus. So applying law of chemical equilibrium, so if we apply the law of chemical equilibrium, so K will be concentration of products by concentration of reactants. So concentration of products is like concentration of H3O plus times concentration of A minus by concentration of Ha, times concentration of H2O. Since water is present in large quantity, so usually we add water in large quantity, so its concentration remains practically constant, so it does not change. So we just omit this one, concentration of H2O of the denominator. The concentration of water may be combined with K to give another constant Ka. So if we take H2O this side, okay, and then multiply with K, we get Ka. So Ka is called the dissociation or ionization constant of an acid. So Ka is H3O plus concentration of H3O plus times concentration of A minus by concentration of Ha, where Ka is called dissociation or ionization constant of an acid. The larger the value of Ka, higher is the concentration of H3O plus, and hence therefore stronger is the acid. So the value of Ka, from the value of Ka we can actually come to know whether an acid is a strong acid or a weak acid, okay, or how strong the acid is. Or other way also we can calculate pKa. So pK will be reciprocal of K because you have minus sign there, minus log Ka. Okay, so from there also we can actually predict whether an acid is a strong acid or not. So degree of a dissociation or ionization is defined as the fraction of the total number of molecules of an electrolyte, acids or base, which ionizes into ions, and it is denoted by A, denoted by alpha. Okay, it is denoted by alpha, not A, alpha. So alpha is the number of molecules ionized by total number of molecules of electrolyte. If C is the concentration of moles of the acid in 1 liter of the solution and alpha is the degree of ionization, then the concentration of each species at equilibrium are. So we started with weak acid Ha and I put water here. We get H3O plus plus A minus. So initially we are taking concentration of Ha is C. Initial concentration of Ha is C and there is no H3O plus and A minus. So we get 0 and 0. At equilibrium, so alpha is the degree of ionization. So for each one mole of Ha, okay, so alpha number of moles will be dissociated. So we get 1 minus alpha is undissociated here. So at equilibrium the concentration of Ha is 1 minus alpha times C. For 1 mole it is 1 minus alpha. For C, concentration of Ha is C, so we are multiplying C here. And concentration of H3O plus is C alpha. C alpha, and concentration of A minus is also C alpha, because the concentration of H3O plus and A minus is the same here. That's why we get C alpha and C alpha for both. For weak acids, alpha is very small, so that 1 minus alpha we consider 1. So in comparison to 1, the alpha value of alpha is very, very small. So we can actually neglect the alpha here. So for 1 minus alpha we can directly write 1. So Ka will be, so Ka is our concentration of product. So we get in the product we get here is H3O plus plus A minus. So here, so we will put C alpha times C alpha in the numerator, and the denominator we write denominator we write only C. So actually Ka we write concentration of H3O plus that we discussed just now times concentration of A minus by concentration of H3O plus at equilibrium. So concentration of H3O plus is C alpha and concentration of A minus is also C alpha, this time C alpha, and then concentration of H3O is 1 minus alpha we considered 1 because alpha is very, very small, we write C here. So this C they get cancel each other, so we get C alpha square. That's why it is written here. So K alpha is nothing but C alpha square. So we get alpha equals to root over concentration of root over Ka by C concentration here. So actually if we know the concentration of initial concentration of Ha, and if we know the value of Ka of a particular acid, okay, we can actually calculate degree of dissociation alpha, okay, from this this expression. Now concentration of H3O plus again is C times alpha. So we write root over Ka times C times Ka by C times C. So we get root over Ka times C here. So we can calculate concentration of H3O plus, and then we can calculate pH, right? So if we take the log of this both sides, we get pH if we know the value of Ka and concentration of C. So next, so the pH scale of a hydrogen ion concentration had been useful and it has been extended to other species. So we may also write pK is minus log Ka. This means that the stronger acid will have higher Ka value but smaller pK value. That's what I was discussing. While weaker acid will have small Ka but higher pKa value. Similarly for bases, since pKb equals to minus log Kb, again I am repeating, so log base here is 10 for pKa, pKb and pH. This means that strong acid, strong base will have higher Kb value but smaller pKb value, while weaker base will have smaller Kb value but higher pKb value.